So I realized last time that I skipped a slide. And so here's some miscellaneous information. Let's talk about spring. So we'll draw a spring looking like this. And when you push on a spring with a force F, it gets shorter. Or if you pull on it, it gets longer. And the relationship for a spring is that the force is proportional to the change in length. And we call that the spring constant. The second thing has to do with cables or ropes. So if you have a cable or a rope, the force is along the rope, so you've pulled it taut, and you can only pull on ropes. You can't push on a rope. So this is not an option. So if you have a rope, this is not possible. Okay, so you have to always pull on a rope, and the direction of the force is along the rope. The next thing are pulleys, and so what we're going to learn later, and we'll prove this, we'll have a little in-class demo, is that when you pull on a frictionless pulley like this, these two forces will be equal, and this third force that the pulley is attached to and hanging from the roof or something, that force will bisect these two forces. We'll learn this later, we'll prove that later, but for now, just remember, in a pulley, the two forces on the rope, if it's frictionless, are equal, and that these two forces are equal angle from the direction of the hanging part of the pulley. So the last topic are smooth surfaces. So if you have a smooth surface, let's say ice, let's say you have a block on some ice and it has a force F on it. Let's draw the free body diagram. So here's the loop. You draw everything that's in there. There's the block, that force F. And we've cut through where the block touches the ice. So you'll have a force normal, we'll call N. And typically you will have a force tangent due to friction. But because it's smooth, there is no tangent to the surface force, and that's zero. So for a smooth surface, the reaction is also always normal to the surface.